right. What's going on? I wanted to continue looking at this Donex ransomware. This definitely has a crypto flaw in it, so I wanted to see if we could write a decryptor. I'm going to show you a few tricks for how we can figure out if things are indeed decryptable. Okay, so just to kind of recap, we took a look at this ransomware sample. We also worked on some new functionality, we worked with some new functionality that was shipped with Binary Ninja Sidekick. And we worked on these scripts that were generated by this analysis workbench. And then so if I open up the script here, some cool new functionality is this LLM operator, which can essentially call out to a large language model and then use the response from the large language model to generate indexes that are then available in this index menu. So we messed around with that. We got a few different cryptography related calls, including the one that was decrypting the ransomware configuration XML. And if we go back to kind of the main function here. So in this MW main, we had that XML decryption functionality that was using these XMEM registers. And then it was finishing off the encryption using this last hex A9 XOR. So then we were able to recover the ransomware configuration, which is in XML here. And then we just kind of looked at the rest of the ransomware functionality. So I took a look at Leon's blog post, and there was a few things that I didn't get 100% correct. So I just wanted to go over those. And I'm sure y'all remember me kind of obsessing over whether this was Cha-Cha 20 or Salsa 20. And if we check out Leon's blog here, Leon identified that this was actually a Salsa 20 project that was being used by this ransomware. But yeah, basically this is a Salsa 20 library that is available on GitHub. And this is separate from the embed TLS functionality that was also being used. So the reason that's important is because, well, not for our decryptor today, because we're going to be using a different technique, but it's important to know what library you're dealing with, because then you can actually compile the library and then diff it against a specific database. So we won't be doing that today, but I'll just link Leon's blog here into the chat. And then I also wanted to link this talk that I saw at Recon, which detailed this crypto flaw. So this was a really good talk that I wanted to share with everyone. And I'm going to put those in the reference notes as well. So if we look at those slides in this PDF, then they basically went over the kind of use of ransomware and building a decryptor for this ransomware. So we saw these XMEM registers last time. We looked at this create mutex check, and then they went over the config decryption. This is all using IDA scripting, so a little bit different than what we did. They went over the XML configuration, which is what we looked at. The key generation algorithm, which we also looked at a little bit. And then looking at the file encryption functionality, which we also looked at. So again, they were able to identify whether it was Salsa or Cha-Cha based on, it looks like, these patterns here. So the constant is the same as Salsa 20, expand 32K. Cha-Cha replaces the Salsa quarter round with this. So I think they're inferring here that it was Unfortunately, the recording of the talk isn't out yet, so I wasn't able to review that. But yeah, based on Leon's blog, I do believe it's Solstice 20. So yeah, so let's take a look at the functionality again, the encryption functionality that's remaining. The one thing I did not go over in the previous live stream was the view of these indexes, which is kind of cool. So I just wanted to look at that real quick. So the Sidekick indexes that we generated using this script, looking for all the cryptographic operations, it will set them into these indexes. And then you can actually visualize the call or kind of like a graph view of these indices using a different view within Binary Ninja. So I kind of mentioned that a few times, but it's called the code insight map. So if I click on that, we can see that basically as we navigate throughout the binary, let's see if I can select the relevant nodes. So these are our available indices. So these are the ones that we generated using that script, these cryptography related calls. So if I click on this, then this is a much easier way to visualize this than that like table that I was clicking through last time. So this is pretty cool in that we have like the function name and then the relevant cryptography related calls. So here we have the address 403. Okay, that just changed it, I think. 40311E. And then we have performing a bitwise XOR operation on memory segments with 128-bit values. This may be a part of a simple encryption scheme. So I believe that was so if I go to this address, I don't know what copy address, if it's actually going to give us that 40311E, but if I split this, or we don't have to split it again because we have it here, I just hit it. 40311E, then we see that's our config decryption loop here. So the AI was able to identify that functionality, and then we were able to visualize it in this code insight map. So that's pretty cool. So yeah, this view is much easier to navigate than the table that I was looking at before, and it has like this nice interfunction relationship between the nodes with these arrows here. Hey Leon, how's it going? So yeah, pretty cool. So if we go back, so one of the big parts of this talk that was very important is that there is not only a key reuse attack, but there's also a limitation of the size of blocks that are being encrypted with a new key stream. So there might be some limitations to this based on, again, this slide is kind of confusing, but we'll do our best. But essentially how a key reuse attack works is, so if we go back to our encryption functionality here, so this was the network stuff, and then this is going to call our main encryption loop here. And then if we look at the main encryption loop, we can see, again, this is identifying all the files within a given directory, and then it is checking if it's a whitelisted extension or a blocklisted extension that it does not want to encrypt. And then it looks for the blocklisted directories and stuff like that, all that stuff from the config that we reversed last stream. But if we scroll down here, so if we get to the point that it wants to encrypt the given file, then it's handed off to, let's see here, this MW read file encrypt data function that we analyzed last time. And so I think this is what I was commenting on the different sizes with the keystream recovery, but we'll cross that bridge when we get there. There's different block sizes. But if we scroll down here, we can see that there is the create file that acquires a handle to the given file being encrypted. We have the set file pointer, which is setting the file pointer to the beginning of the file. It then reads a given block length from the file, and then it passes the resulting buffer from read file to this MW cha-cha-20. So since we now know that this is salsa20, we can rename this to salsa20, and I'll save that. And then we have this global key here. So the fact that this global key is generated in the main function. So if I go back to, let's see, MW main, where this variable is assigned in the high-level IL here, where this global variable is assigned, we know this was our MW gen enc. So this is the key generation function. So I'm just going to call this MW gen key. And we know that was the key size being passed as the parameter here, which is 16 bytes. So this is using a 128-bit key, or 16 bytes. And then this is the key initialization function for the ransomware. And since this is a global key that's only being generated once within this MW main function, and then it's used in a global variable, this ransomware is vulnerable to a key reuse attack or a known plaintext attack. Yeah, I'm good. Thanks, Leon. Just looking at all this different research that y'all did. So if we go back here to where this global key is used, then we can see that if we go, this might be different. But yeah, every call that is made to this MW salsa20 that actually performs the encryption functionality. And then this is passing this function pointer here and calling it. So we can actually mark this up. So we have the global key, and then this is going to be, I don't know why the file is being mapped in this instance. And then in this read file encrypt data, it's being read using read file. So I wonder in which circumstances the mapped file view is being used here. Let's see. Maybe this is encrypting the... We can probably confirm that dynamically, because it looks like this functionality is quite similar. But yeah, TLDR, basically this global key is always being passed to this MW salsa20 function. And then because it's never getting a new key, then the same key is being used for each encrypted file. And then because the cha-cha-20 algorithm is a stream cipher, we can actually XOR to a known plaintext file with a encrypted file, recover a keystream, and again, this requires us to know that there is a plaintext version of a file that we can XOR with the encrypted file that was encrypted with this generated key. But if we can recover that key stream, we can use that to decrypt other files because the same key was used. But yeah, basically, if we can confirm this dynamically, then we should be able to write a decryptor today. So let's look at that. So if we go back to our main VM here, then we should be able to run this ransomware against two separate files and then see if they have the exact same ciphertext. And then that will confirm that we indeed have a key reuse vulnerability here. Okay, so first let's generate two separate files. And then we can encrypt them using the ransomware. This is just like a rudimentary test. So I've already set up a snapshot for my setup here. And typically what I do is if I'm running anything dynamically, especially like ransomware, I'll ensure that there's no writable shares. So I don't have any writable shares because ransomware, including this one, will enumerate mounted shares, including network shares, and then it'll encrypt them. And another thing I'll do is just set up the environment. So I have my sample already here And just so if I restore snapshot, then I don't have to like recopy the malware file and then like restart everything. So that's basically what I've done here. So the next thing we can do is just open up Python here, and I'm just going to do this in the C directory, so these files are encrypted right away. But if I just do Python, then we'll just do f open a.text and then f write, and we'll just do like a bunch of A's. So let's just do 1024 A's and then close, and then we'll open up another text file, and then we'll write the same amount of A's to that file, and we'll close that. And then if we look in our C directory, we'll have those text files, and text files are indeed targeted by this ransomware. So they will be encrypted when we run this. And then now that we've kind of verified all of those steps, then we can run this ransomware. So I'm just going to go to the desktop here and then go to our folder. And then I'm just going to run this. Actually, maybe I'll run it in a debugger so then we can terminate it once it encrypts. So I'm just going to open up X32 debug here, and then I'll open up our sample, and I'm just going to change the extension here to .exe, even though it's not really needed. Okay, and then I think we should be good to go. What I actually might do is, just so we can look at some of this dynamically, is this font too tiny or is it okay? In X32 debug. And then let's take a look at our database again, and let's rebase this to the same address within our X32 debug session here. So I'm just going to go to follow in memory map. And then this is the base address of our current ransomware sample. So I'm going to copy that address. And then I'm just going to go into Binary Ninja and do edit. Or sorry, it's analysis, I believe, and then rebase, yeah. And then I'm just going to rebase it to the same address here. Okay. And then I'm just going to take another snapshot so we can restore our debug session. So pre-Donex dynamic or something like that. Now that snapshot's done, let's break on this encryption function. So this 64285B. Let's look at the disassembly here. Yeah, on this create file call. So I'm going to set a breakpoint on that create file call, and then I'm also going to set a breakpoint on that other encryption function. Again, not completely clear what the difference is here. Maybe if it can't get access to the file, then it calls this function, because this is doing the RM start session stuff. And then we'll do, I think it's getting a memory map of the file here, so we could probably do the call to create file mapping. It's probably best. Or create file here. Yeah, let's do the create file call, because I think it needs to get a handle to the file before it can get a mapping of it. Okay, let's hit that. Okay, then we have our first hit on create file here. This is the 643B3F. So that's this function here. And then we don't really have to step through this entire function, but basically it's going to map the view of the file and then encrypt its contents using this call to MW salsa20. And does it just get a full buffer when it maps into memory? LP base address. I have to figure out which one's the length here for our call to salsa20 here, so it might be easier in the other function. So we have this Boolean, which I believe is related to the salsa20 library and the key length. And then I don't know what this var28 is, but we have 1, 2, 3, 4, 5. So this is the LP buffer, and then this is going to be our buffer size. Okay. And then if we look at the other call to this, then we should be able to see now which is which. So this is the buffer, this is the size, And then this is our bool, keyline bool. Basically, I'm just marking these up so I can see where they're used. So the LP buffer comes from the map view file, okay. And then the memory mapped view address. What does this struct look like? So if we look at, oh wait, shit, this is Rust. Is this struct not open source? I mean, sorry, within MSDN. I guess we can infer from the, let's see, the return value is just the starting address of the mapped view. Okay. And then the size. Okay, so it's, okay. So yeah, it's just mapping the entire file into memory and then encrypting it all at once using the salsa20 call. So most ransomware doesn't do this because if you like load a file that you're encrypting that's like multiple gigabytes in size or something, then you could use up all the memory and then freeze the system. So kind of interesting. I don't know, I don't quite have a handle on the logic as to why, oh, is that the only, okay, so this might be a part of the multi-threaded part. Okay, whatever. So, okay, so now that we know the parameters for our salsa20 call, again, we don't really have to go through that. I just kind of wanted to see exactly how that worked. And then, so now if we go to this proc, if we go to this file path in EBX, we should just be able to see it be encrypted. So this is extended ASCII. So if I just copy this guy, binary edit, I usually find this is the easiest way to copy the text in x64 debug. And it's being a pain because it's UTF-8. So let me try that again. Maybe I'll just do copy selected lines. Okay, so this is where the file is being encrypted in this tools directory. And it's this proc.zip thing, proc.zip file. So it was moved, but I think this is still plain text at this point in time. So yeah, it's PK, so that's the zip magic. But then if we let it encrypt the file, then now we'll see that this should be ciphertext. So I use like HXD. The ransomware still has a handle to it, so that's okay. Let's just keep this running. So if I keep hitting run here, we can just see the ransomware encrypting each file. So this is going to take forever, but I'm pretty sure we shouldn't have hit our files yet. Yeah. So maybe I'll just let this run without hitting these breakpoints. And then we'll see our files being encrypted. So before I do any of this stuff, again, I just check the shares and make sure nothing's connected. And then this also doesn't have network connectivity, so it's host only. So I'll let that run. So we can see, oh, we hit something. Access violation, that's probably fine. Hopefully the ransomware is handling that. I didn't change anything, so it should be able to handle it. Let's see, run pass all exceptions. That's what I want. So Control Shift F9, you can just pass all the exceptions to the ransomware. Okay, so it exited, but our files aren't encrypted. I don't know why. Maybe there's a bug in the logic or something. But all of these are encrypted, it looks like. Okay, maybe I'll run it again and then just put the our text files in this tools directory. That's pretty funny. Maybe it might be block listing the C directory, like the root one. Okay, and then I'm just gonna run this with, again, the ability to pass all the exceptions. Okay, maybe it's not encrypting text files. So let's just rename this to like any of these other extensions that are being targeted. So like .py. I should have looked closer at the block list before I just assumed it was encrypting text files. Okay, we should see those encrypt. Unless I just need to start over. Maybe I'll just restore my snapshot and then just make them .py files. All right, Let's try that again, but this time we'll do .py, and this should be running as, oh, maybe that's the problem, is the UAC permissions. So the icon that we looked at last stream that we took out of the config, I didn't actually make it into an icon file, but that's what it looks like. It's this D, which is kind of cool. Why is it encrypting these test files? Maybe I'll throw them on the desktop. Oh, I restarted. Yeah, pretty good. Okay. So this is the that shutdown command that we also looked at. So now it's restarting. So let me see. I'm just gonna restart the snapshot, and let's see if we can get those test files encrypted. It's definitely not checking the magic or anything. So put these on the desktop, and then we'll restart this as administrator. I'll let this run. It's actually really weird that it's not encrypting those. Very curious. Like, how big is this XML? We can just use this XML file, but it's just really weird that it's maybe it's not big enough. We could probably reverse it more to understand the logic, but it's kind of like so they're encrypting these command.exe profiles. Okay, let's it might be the size. Okay, let's try doing like a meg. Okay, let's try aa.txt, and let's write fw.write a let's do 100,000, or not fw, but f.write. Okay, and then we'll do bb.txt, and then do the same thing. Okay, and then again, let's put all that on the desktop. Let's make them XML, because I know, okay. And again, we're gonna restart this and run it. There you go. Do you see those encrypt? So now we can kill this. And then if I open these in HXD, then we can see they have the exact same ciphertext. So what that means is the key reuse algorithm that, or sorry, the key reuse attack, or the key reuse vulnerability rather, that is within the code is indeed occurring when we run it dynamically. So how can we exploit this? So again, because it's a stream cipher, we should be able to XOR this with a known plaintext file, recover the key stream, and then decrypt a given file. But there is one more piece of this vulnerability that's quite interesting. So not only are they using this entire file encryption functionality in some instances, or no, sorry, this is the other one. So when there's this encryption function, every time it encrypts a block, then it doesn't, basically it resets the key state to the original state. So if we look at the length here, so this LP buffer that's being read, and that's this block length that's being set up here, then basically if we know 1 meg, or like approximately 1 meg of the known plain text, we can recover the key stream and then recover all files that are being encrypted using this block algorithm. So it's not only vulnerable to a key reuse attack, but because they're resetting this salsa 20 state within each block, then basically what we should see in theory is every hex 100,000, we should see the same block pattern in the like repeating A's. So what I wanted to do is confirm that theory also using dynamic analysis by seeing which files are being encrypted with this technique here. So if I go back to the main encryption loop, then we should be able to figure out when this is called and the other one is called. So we have like the threaded functionality. So is this just for network shares? That might be the difference. Yeah, okay. So the difference between those two functions, the one that's mapping the entire file into memory and then encrypting it, or the one that is doing those block by block encryption steps, I believe is the fact that one's doing the network share encryption and one is not. So if we go back here, so we might need the entire, like basically the length of the target file that we want to encrypt using the other method. So that might be why it's not as simple as I originally thought. Okay, so does that make sense? Does anybody have any questions? Pretty quiet. All right, probably just keep going here. Okay, so if we look at the non-network share encryption, then I should be able to confirm what I was talking about. MW enc main, enc file is what we want. And again, this is the threaded one. So like in theory, we shouldn't see, so actually let me confirm that the other one is only being called for network files. Actually, whatever, we can just work with what we have here. So let's work on that keystream recovery so we can automate that. So we can just do the A's example, and then maybe we can try and see if we can optimize this. But if we look at this function, then we have the file handle that's acquired, the view is mapped, and then yeah, the entire file is encrypted. So that's fine. And then the ransom node is written to the given directory. So the next thing we can look at here is recovering this keystream. So in this instance, it's very trivial because we know it was 100,000 A's. So we can basically just write a really quick script to recover that keystream and then confirm that this is indeed vulnerable to a known plaintext attack. You kind of always want to confirm your assumptions and then like move forward with them. So let's see if Python is still working on this because it might have been messed up. Okay, I think Python got borked here from the ransomware. But maybe what we can do is copy these two encrypted files locally, and then I'll mess around with them there. And then we can just mess around with these locally on my host, which does have Python that's working. Okay, so and then once we recover the keystream, then we can use it to decrypt other files on this disk. Okay, so the first thing that I'll do, we don't really need that terminal right now. I'm just going to open up a new file, Python 3. Here, I'll make this a little bit bigger. And then literally all we need to do is import sys, and then we'll just do sys.argv, or if the length is less than, we'll take 3 parameters. So we'll just print out, I'm just gonna write this in Python because it's the language I'm most comfortable with, but maybe we can port this to something like Golang so it's like faster. But for this, I think this will work. And then we need, we'll just say the second file to XOR. I guess this isn't a great name, but we'll just rename it later. And then we're just going to have a separate function that's just XOR files, or we'll just call this recover keystream, I guess. And then we have first file, second file, and then we're just going to read each one. I guess we can do this in a separate function. And then we'll just do fopen, fpath, f.read, and we need to open this as bytes. And then we'll do read file first, read file second, And then we're literally just going to do first, second, and then these will be the bytes of each file. So we'll just do 4B, we'll have a resulting bytes object, and then we'll just do B, we'll just do enumerate, and then so we can get the index. And then XOR with second I 2 bytes 1 little. Okay, so then we and then return R XOR first, second, and then we'll return our keystream. And then let's see if the script works. First is equal to sysarg v1, second sysarg v2, and then we'll recover keystream first, second. Okay, we'll do keystreams equal to that. I'll just do print keystream 256 bytes, and then we'll make that hex. Okay, so I'm just going to make sure that my code doesn't suck. I'm just going to save this to the right place. So we have stream, cover stream.py. Oh, I forgot length. Here. Wait. Here. And then we'll do our first one and our second one. Oh, did I do append? I meant to do plus equals. Unsupported types for string and string, but they shouldn't be strings. Did I mess this up? Read file. Oh yeah, I did. Byte order, not ending. Right, that makes sense because we're not using, I just XORed them together, which equals zeros. So we need our original aa.xml and then do fw or f.write and then f.close, and then we'll do our aa.xml index out of range. How big is the oh, it's because the original is 512. So I think they're appending the encrypted key to the encrypted file, so that adds 512 bytes here. And then so we want to do, I think we just need to change up our length stuff here, or we just do up to 512. I'll just do that. Enumerate first, and then we'll just do slice it. Is that how I do it? I can't remember. And then, so just like double confirming my slicing. Okay, yeah, so that's correct. And then maybe we'll specify that the first needs to be our encrypted file, and then the second needs to be our known plaintext file. Okay, so in theory, this is the recovered key stream for up to the size of our aa.xml file, which is our test encryption file. So again, in theory, we should be able to copy any other file from the system and then be able to decrypt it. So let's do this config.xml. I don't know what that's from, but I think it's probably from Flare VM. And then basically we just want to modify our script here to be encrypted file, known plaintext file, and then we'll have target file to decrypt. Then we want to make this 4. And then the next thing we want to do is recover our target file. So then once the key stream is recovered, we'll just have key stream our target file. Then we'll do read file. So our ciphertext will be read file target file. Then XOR our key stream data. I guess we need to modify our XOR function. So let's do def XOR, and I'll show you why in a second. Or CT. I'll just copy our code from before. But the reason that I need to do this separately is because, well, first we don't want to truncate this CT, but we need to mod the key stream length for the length of the file. The key stream is obviously like a meg in this instance. So if this file is over a meg, I guess we only want to iterate for the length of the key stream, not the CT, because we're only going to be able to recover up to the amount of the key stream. So we'll enumerate the key stream and then CT and then return R. But the other thing that might happen is the key stream is larger than, okay, let's just enumerate the CT. And then we'll just mod it for now until we can figure out that other logic with the length of the key stream. And then XOR with key stream. Then we'll do key stream CT. Double check my code. So for B and CT, then we're XORing it with the key stream with B and then appending it to R. So this should in theory be our plaintext. And then we'll do file data and R. And then let's print this out again, same kind of thing. Okay, so let's run this. And then we have our config. Oh, we want to actually print that out. Not in hex, because this should be plaintext. And there we have it. We're able to recover that XML file using a known plaintext tag, or at least up to the key stream length. So I don't know what this this little bit is here, but then we get the rest of the plaintext file up to the size of the ciphertext length. So I'm curious as to whether or not that other function is called, or basically they're always going to be mapping that entire file into memory, and whether or not we can basically recover the largest key stream possible using like Windows default files. Oh, actually, this might be. No, this is the entire config file. Okay. Yeah, because this is the start of the XML node. So that's cool. Okay, so I'm just going to do a, looks like UTF-8 bomb. Okay, cool. Hey, Dimok, how's it going? Good to see you. Okay, so now that we've written our recovery script, I kind of want to evaluate what we can do better and then see if we can port it. And I also want to see if that network encryption function is called ever for this stuff, but I suspect it's not. And essentially the best we can get is the largest key stream that we can recover on a given system will be the size of the file that we can recover, but we'll see what we can do the best way possible. I'm wondering why. Yeah, so I think the other encryption function is used for the network share encryption functionality. So if I go back to EncNet, then this is like enumerating the network shares. And then this will pass it to the main encryption loop. Oh, maybe hold on, let me just like triple check that. MW enc net main enc loop enc main. Maybe I need to fix up some of these. So the threaded functionality. Yeah, maybe I misspoke. But yeah, I'm just gonna run to the washroom real quick and then we'll confirm that. All right. Looks like there's some good discussion going on in the OA Labs Discord live channel about this stuff. But yeah, let's confirm where the alternate encryption function is being called. Because if we can do, like, I guess I can just confirm that dynamically real quick. If this is ever being called. Because this one's like, or sorry, not this one, the other one. Let's just look for the cross references of Cha-Cha. MW salsa 20, or not Cha-Cha, but salsa. Read enc file data. This is like the super broken one. Main enc loop. And then enc file is called from the multi-threaded stuff. So when does it use the multi-threaded encryption instead? Is that a config option? I think it is. Let's look at the ransomware config again. So because what we could do is like mod it to not use it. Kill processes, local disks, walk threads. Yeah, it's like not explicit. It just has the number of walk threads, I believe. So I kind of want to see if that other really broken encryption function is ever called. Otherwise, we'll just improve our current script. So let's run that again. Maybe I'll save this so we don't have to deal with another key and like multiple new files. So I'll just do Donex, lots of snapshots. And then once that's done, I'll restore. And then we'll let it encrypt again. Okay, that's done. So I'm going to do that. And let's see if this super broken one's being encrypted, or sorry, being called. I think file, we can call this MW salsa 20 because it's not Cha-Cha. And then, yeah, so let's just set a breakpoint on this address, 64260. Oh, wait, let me restart this as admin too so we can encrypt everything. Cool, and it's the same base address, so let's let it run. Quick and dirty method, but it works. And while it's running, yeah, it looks like it's not going to hit. Check white extension. Do. Why is this in a do while? Okay, it's just doing the find first file with a do while. Yeah, it looks like it's only called with this network encryption functionality. So that was right. So it looks like the kind of largest file recovery approach is the only one we can really see here to improve upon. Yeah, so it restarted without hitting our breakpoint, unfortunately. So let's go back to our already encrypted system. And I guess we could start with a plain text one here. But basically what I wanted to do is look for the largest file we can find on disk that is basically a known plain text file, so like installed by default on a given Windows system that is likely recoverable. And then hey Xerox Falcon, thanks for the follow. And then once we have that largest file, then I just want to write the code to decrypt all the files as much as we can on disk effectively. And then maybe we can port it to something, but just because Python's broken on this. So basically, in order to run Python, I would just have to get a Python environment running on the encrypted system, like by shipping one portably in a portable fashion, or I could probably figure out another way. But okay, so let's improve our code here. So what we want to do, I guess we don't really need our Python code right now. We could write something in Python to look for certain types of files, or we could use something like PowerShell, which is kind of what I was thinking, because it's good at just recursively enumerating for different extensions and stuff. So maybe let's just do, I'm going to need AI assistance though, because I'm not super familiar with PowerShell. To find all files with specific extensions and sort by their size. Okay. So recurse include sort by length. Okay. Pretty straightforward. Hopefully PowerShell is not broken. I guess we can do this on a clean system. This is kind of silly to be doing it on the encrypted one. So like kind of the theory here would be that you would have a store of known plain text files within like an enterprise environment or something. Or you could make this as like a service where like a program would look for these known plain text files on an encrypted system. And then if it is able to recover or if it is able to find a file with the same file name as a known plain text file that you have, then you would recover the largest key stream possible and then use that to decrypt the file. So let's open PowerShell and then let's recursively enumerate all of these files with that line, if my clipboard works. And we could probably look for like JPEGs. What other stuff is it going to be encrypting that's going to be large? Doc files. I guess I could do docstar. PNG files. Does anybody have any other ideas for large plain text files that it could be encrypting? XML. Or maybe even a better technique would be to exclude the block listed files that are in the XML. Let's do that. It's a little bit more kind of work smarter, not harder thing. So, yeah, it's all these. So I'm assuming we can do like a exclude in this get child item here. Well, let's see if what Copilot says. Excluding. It actually used the ones I'd selected in. Damn, that's sweet. Did you just see that? So it highlighted this section of the code or of the config. And then I put that question into Copilot and then it spit out the script. That was pretty nice. Okay. And then, so let's use this. And then can we do this all in, no, we're gonna have to put it into a PS1 file. That's okay though. There's idle or whatever, or no, that's the ISE. That's what I was thinking of. And then new, and then we'll just recursively enumerate. C backslash. Let's call this like get clean files or something. .ps1. And then, sorry, my mic stands being annoying. And then we'll run this. Filter where object. Yeah, basically it's just excluding those files. Okay, let's let this run. It's probably gonna take a while. Oh yeah, and I guess I should have ran this as admin. Where did I save this? Oops, I did not mean to do, we need the integrated scripting environment running as admin. And then let's run this. Might take forever, but still getting unauthorized exceptions, but I think that looks like it's Defender, so maybe Defender doesn't allow you to access those directories. This is probably gonna take a while. I guess in the meantime, we can work on our script, right? For me, it is interesting. Cool. Oh, I do like it. All right, so basically we're going to do, like we're gonna make this for the full system decryption. So I'm just trying to think, because we want to make it find our known plain text file. And then we want to use that found encrypted plain text file as our target file to recover the keystream with. And then once we recover the keystream, then we want to recursively enumerate all files within the system that are encrypted. And then we want to decrypt all of those files up to the keystream amount. So let's write that. So let's do, again, I might get some AI help here, but recursively. So we're going to need like a global, or like our config that contains all of our plaintext file names. So we'll just have like, we'll have them there, and then we'll just do def enum pt files, and then we'll have our plaintext files, and then maybe we can provide like a starting directory to recursively enumerate. I'm just going to turn on my little copilot here. Maybe I'll just use the chat. Enable completions. Let's see if that works. os.walk. And then ends with for files and pt files. Now we actually want to enumerate for files and files ends with. So we want this to be os.walk. What does this return? Iterator containing 3 lists, the directory path, the directory names, and file names. So we want the file and file, yeah, that's correct. And then for pt file and pt files, if pt file in file, yeah, that's correct. Then we want to get our matched files, and then we'll do matched files dot append, and that's joining the root with the file. I think that's fine. And we want to return match files, and then it's pretty clever. Def recover all files. Start directory. Because this is going to be pt file in file. Yeah, that's correct. Because basically we just want to make sure that, because this is going to be, the plaintext file name is going to be a substring of the file that's encrypted, right? Because it's going to be have that appended extension. And then let's see, recover all files, flag secret. Yeah, it's so weird sometimes. So we want to read our, keystream. Or no, wait, this is like, we're kind of getting our head of ourselves here. Okay, I might just kill the auto completions because they're just annoying. Disable completions. Okay, we'll do def. Okay, so once we identify a known plaintext file, or the known plaintext files, then we want to recover the largest keystream possible. So like in this pt files list, we need the size as well. That onion. Hello everyone. Hope you guys are having a lovely day. Yes, thanks. We are having I'm having a lovely day so far. Thanks for joining. So let's do def get largest pt, and we'll do matches, and then maybe we can have like, this will be like a list of the file name. So this will be a dictionary of the file name, the locate or the path to our plaintext file, and then this will be the size. I guess we can acquire this, whatever, we'll just have it. Yeah, let's just have the those dictionary elements, because maybe we should pre-compute all of the sizes on the fly at the beginning of the program, so that we're not doing on each iteration, which we can do, that's fine. Maybe we should make this a JSON file or something. We don't even need to do this, right? Like this will be the config format, but we just need a known plaintext file directory. Like these are a lot of config params, but whatever. Like eventually maybe we want a config file rather than just having like 5 configuration parameters. So maybe, okay, so this will just be for match in matches. And then this will be our PT files. And then for match, if match, PT files, like maybe we want this to be a dictionary of the file names. Yeah, whatever. Match, and then file in PT files. We can just adjust these later on. If match is equal to PT files, or if match, can we do this a smarter way? Because we already have this information. I think we can do this smarter. So we'll do largest is a very low number, and then our match files. So we'll just do if match, if PT. Yeah, we're gonna need to change the PT file name. If PT file size greater than largest, then we want to append it. And we don't really need this as being a list anymore. It'll just be the matched file. It's none. And then this will just be equal. So that's a lot smarter because we're not like redoing, we're not going over all those files again. Matched file. And then this will be an if statement. Matched file. Okay. And then we're going to populate this dynamically, but it's going to have, let's do this file name and then size. Yeah, well, that didn't work very well. It's just printing them out. So we'll do sorted files. We don't really need a table. Yeah, it looks better. Okay, let's run this again. Maybe we should have this written to a file because it's gonna be huge. I think it's like out file, right? Let me just double check. Yeah, it was out dash file. And then out dash file path. And what is output file path set to right now? Nothing? Okay, cool. Yeah, it's just sorted files.txt. And I'll just write this to C:\\, just need 2 backslashes because it's a string. I don't know. All right, hopefully that works better. We're gonna have to collect these, but I'll probably just do like the top X amount of files. So the next thing I'm gonna do is continue with that script. So we'll do, okay, matched file. So it's gonna be the largest file that it is in theory encrypting. I kind of realize now this might reside within one of the block listed directories or something, but we'll just go from there. What are you doing, man? Writing a script to automatically decrypt files that were encrypted by ransomware. That makes sense. Also, how's it going, Pidge? SSAA. Uh-oh. Is this gonna take up too much memory and crash? Okay, let's finish this. So once we find the largest file, so we'll do enum pt files. Actually, yeah, enum pt files. Then we'll have our, what do we need here? We need our pt files. And then our start directory. So this will just be, let's just hard code it to C:\/ for now. And then once we find our matched file, that will be what we're using for our known plaintext file. And we actually need in addition to the matched file here, we need our encrypted file. Our matched file would be our encrypted file here. This needs to be this content. Good luck with promotion. Thank you. Appreciate it. I'm just trying to think. Yeah, matched file will be our PT file name. I guess we want the full OS path, but without the encrypted file name. So we want this to be our root, os.path.join root. Hopefully this works. I don't know if this is correct, but it might be. And yeah, thanks for the follow, Danny Boy and your fom. Appreciate it. Okay, so matched file, encrypted file, and then we'll return our enc file. And we need to have, okay. So then we'll have enc file, and then, this is getting to be large. And then what do I do next? Okay, once we find the files, then we need to recover the key streams, right? So we have our keystream, recover keystream. This will be the enc file, matched file. And then now we need to write our function to decrypt all the files that are not with, or I guess we already have the extension here. So we can do enc file split on dot, and then we basically want the last one. Maybe I'll ask AI what the best way to get the last file extension is. Split text, file name. Okay, it's just, I think splitting on dot's fine. And then the last element, it's just -1. So enc extension, then we'll do decrypt all files, keystream, enc extension. Then we'll basically do the same thing as here. So we'll walk our starting directory, and then we'll recover the file data within, or I guess if for file and files, if file, I guess I can do ends with, but in is fine. If the encrypted extension is in the file name, then we want to recover file data, keystream. Is this reading the file? Yeah. And then maybe we'll do, hey Simpson Dev. So it uses Salsa 20 for encryption. We basically reverse engineered the whole piece of ransomware last stream. And then this has a crypto flaw in it, an encryption flaw in it that allows us to, if we have like a known plain text file, then we can recover the key stream that was used to encrypt all the other files and then decrypt a bunch of files. So that's what I'm doing right now. But yeah, basically it uses Salsa 20 to encrypt files. And it's written in C. So I use this program called Binary Ninja to reverse engineer the ransomware. And then we could see in the ransomware that there was a global key that was being used for each file. And then because it's using a stream cipher, Salsa 20, then we can recover the key stream and then use that to decrypt files. So, okay, so recover file data. Hopefully that makes sense. If you have any more questions, just let me know. Our data, and then let's create a new file. That is a different file name. So we'll do file, os.path, join root file plus .rec. So we'll just because I don't want to overwrite the original encrypted file yet, just because this might not work off the bat. And then we'll do WB because it's a byte file, and then f.write our data, f.close. I think that's all we need. Cool, I'm new to cybersecurity, so I barely know these algorithms, but it's fun to hear about them. Cool, yeah, nice. Yeah, like encryption algorithms, there's like standard implementations that you can look at the code for if you've done some programming. A lot of the like actual code implementations aren't super straightforward, but yeah, it's definitely fun to look at for sure. Okay, so hey SMer, how's it going? Keep the good work. Thank you. Thanks so much. Thanks for joining. Thanks for the follow. Appreciate it. Okay, so now that this is done, let's check on our, okay, so this should be done. So let's see if we have that table that we wrote to our C drive, 55 megs. Okay, so the largest ones are gonna be, let's see, awesome work labeling, current, labbing, sorry. CCNA, I can only hope to be as knowledgeable and talented as you. Oh, thank you, Ruben. Appreciate it. CCNA is really good to get started with, just because you'll have foundational knowledge in networking, and then you can work your way up from there. So it's really good that you're doing your CCNA. I did like, I think 2 of 3 parts of my CCNA when I was in school, and I should have finished it at the time because it's a good designation, but yeah, c'est la vie, I guess. Okay, so these files are pretty big, so I think we should be able to recover a lot of plaintext files, which is cool. And I'm really glad I did the kind of exclusion approach instead of the inclusion approach, because so we have like this Chrome 7-zip file, so this could be really good. But yeah, I'm glad I did the exclusion approach, just because I wouldn't have had like these 7-zip extensions and stuff in my list, so that's good. Okay, so let's check out this Chrome installer location. And then, okay, let's copy this. So maybe I'll do like the top 10 files, and then we'll go from there. So like this Chrome 7-zip, do you have LinkedIn? Yeah, if you check out the invoke RE, so invoke space RE on LinkedIn, you can, you'll be able to see my posts and stuff. Maybe I'll zip all these up. I'll copy them into I'll copy them into a directory, and then we can zip them up together, and then I'll put them on my host before we encrypt the system again. So I know I'm doing this all in the GUI, but whatever. It's only 10 files. So let's do PT files, and then let's do this source.zip and the Java SDK. Again, these wouldn't be here by default on a normal Windows system, but this is just like an example scenario. Source.zip. Let's see what else we got here. Proc. Under tools. Let's do that. I think the proc.zip. Yeah, this is what we were looking at earlier. So that's a good one. We don't really need 10. But I just kind of wanted to make this a kind of more realistic scenario. If there's more like systems that wouldn't have these files in them, kind of thing. So this INI file in Sigwin. I wonder if these .lib files are actually going to be encrypted, because those would be present. Like this is a part of WinDebug, but like this ETL file is big, and this frida.pyd files. Maybe let's try the frida one. I don't know if it was encrypting PYD, but it should in theory, because frida. I don't even know if frida was on here, to be honest. Yeah, maybe let's do the like top 5 that I think could be useful. Proc. Let's do this net standard.xml one, because like these .net files would be on a Windows system by default in theory if it had .net installed. So Simpson said, yeah, I only know some stuff about AES for now. I mostly done things around web vulns. I'm trying to learn some reverse engineering. I don't know a lot. Cool, nice. you're in the right place for reversing. So I know we're doing Python programming right now, but Ruben Rojas, thanks for the follow. Blackburn, thanks for the follow. Appreciate it. Okay, so the next thing that we're gonna do, sorry, I was gonna copy that net standard file. .xml. Okay, so these are kind of like our plaintext files that we can use to recover the largest keystream. So like this Chrome one is 378 megs. So if that actually gets encrypted, we can basically recover every plaintext file on this, or every encrypted file on the system. Yeah, you'll get better with practice and watching these streams and stuff. Everybody starts somewhere, so keep it up. Okay, so I'm gonna copy this into a zip file, and then we'll use that, and then hopefully this just all works. But it might take some trial and error. And I'm gonna see if I can preserve the Python environment by like changing the path or something. And then yeah, I'll probably port this to like Golang or something, so it could just be like a single portable executable. Okay, so now the pt files.zip is created. So I'm just gonna copy this to my host. Okay, that's done. And then we have our pt files here. And then now in our recovery stream.py, that's gonna be the provided. So we don't actually need any of this stuff anymore. We just need the known plaintext directory. Oh, and we need, I guess we don't really need the extension, which is kind of cool with how this decryptor works, but we'll see if it works. But yeah, once we have, okay, so I'll get rid of this stuff. And then, so we have our plaintext directory. We're going to need to enumerate all of the files within that plaintext directory, recover their file names, etc. So then we can populate our kind of initial configuration. And then, so again, we're just going to walk these, and then for file in files, we need to get the file size. I just can't remember the API, but it's just faster if I do it with this. But get size, file, and then we want the these to be within a list, and this is too far over. I'll just call this, yeah, that's fine, whatever. Found files, and then we'll get the file size. What did I say earlier? Size, file name. File name will be file, and then path will be os.join, ospath.join, yeah. Root, and then path, no, and then file. And then we'll return our found files. Okay, so we want to call this at the beginning with our plaintext directory, so we can test this locally without having to be on the Windows system. We'll do our, we'll just comment these out for now. We don't want the REPL. Okay, and then let's get rid of this. Okay, so now we have, we can indent this a little bit, yeah. Okay, so let's see if that works. Recover stream, and then we'll do pt files. No such file directory. What do you mean? No such file directory, Chrome. Because this needs to be os.path.join root. Okay, so now now we have a dictionary of the file name, the path, and its size. So that looks good. So now this is when we need to run it on the encrypted system, but we still have to do decrypt all files. We need to provide the keystream, the encrypt, and the start directory. So we'll just do /. I guess we can do that as a config parameter as well. Okay, so let's just go over our logic here. So we get all the plaintext files, then we enumerate the entire system for those plaintext files that are encrypted. So we could probably fix that user or that function name. And here we're walking for each plaintext file. We get the file name. We check if that is a file within the given directory, and then we look for the one with the largest size. And then finally, we recover the matched file and the file in its encrypted path, and the plaintext file name in that path. For this, we actually don't want the current one. We want pt files, or pt file file path, or just path, not file path. Okay, and then so we return that, and then we get the encrypted file and the matched file. Then we recover the keystream by providing both those file paths to recover keystream, which reads both the files, XORs them together, and gets the keystream. And then we use that large keystream to decrypt all the files up to the size of the keystream. Again, this will be the, okay, yeah, I think that's fine. Okay, cool. So let's see if this works. So I'm just trying to think of how we can package this and see if we can recover files without botching the Python environment. So I think the Python environment will be under, okay, I'm just going to save this PowerShell script because it was very useful. We'll put that in our notes after. And then I'll save this table as well, actually. Okay. And then we have our sorted file table here, because I don't want to run that script again because it took forever. And then I need to package this up. So we'll do zip -r. We want our recover stream, or wait, let's call this recover stream.zip. We'll do recover stream.py, and then our plaintext file directory. And I think that's all we need. Okay, now we have our little ransomware recovery package in the recover_stream.zip. So I'm going to kill this snapshot and go back to our encrypted system. I'm just trying to think. We could probably just encrypt this one. Actually, no, I'll just go back to the setup we had. Pre-Donex, and then we'll see if we can protect the Python environment on here from being encrypted. So I don't remember how to get the Python REPL sys.executable. Okay, sys. Why is it not working? Oh, it's because it's a string. It's an attribute. Executable. Okay, it's just under C Python. Oh, is this the? Yeah, it's well, it's getting there. We still have to test it. It might not work. So I'm gonna put this under one of the Windows paths so it doesn't get encrypted. We use the ransomware's logic against it. I don't know why this is so slow. This is all local. I think the C:\Windows path is block listed. Let's see, white folders. Maybe I should put it under program data. Program files, rather. Microsoft. Yeah, maybe not. Oh no, Windows, yeah. Right here. So that should work. Yeah, Leon, I'm trying to protect my Python environment from being encrypted so that I can use it to decrypt all the files. Okay, maybe while this copies, I'm just going to take a quick bathroom break. So I'll be right back. Drank too much coffee. I made it with Suno AI. Could you tell? I have a bunch of other ones that I could show, but maybe later. Maybe once we're done. So I copied that Python, and then before, I'm just gonna take another snapshot. Or I'm gonna copy over our little decryptor thingy. Okay, and then I'm gonna take another snapshot before I encrypt the system, so I don't have to do all that again. And we might have to modify the environment. Yeah, by the lyrics, the terrifying thing is that if it wasn't singing about IT, I would have thought it was a human. Do I need a subscription for Suno? No, I think you get like a few free songs a month, so you can try it out. It's pretty sweet. But yeah, I'm a musician as well, and it also terrifies me, Simpson. But it's fun to make songs for this stuff. So now we'll do the encryption, and hopefully it encrypts that Chrome path. So then we'll cover basically every encrypted file in the system, or at least all the ones under 300 megs. We can probably figure out what that path was from our stuff that we copied across. I should have done pass all exceptions. Okay, I think it's done. So let's check that Chrome path. So that was the sorted, and this was under the install directory for Google Chrome. So this is a pretty realistic scenario because, shit, I didn't encrypt it because it's in the program files directory. No. Okay, let's check the other plaintext files. We're probably still good. Where is it? Under Windows. Apparently you can do 10 songs a day with the free tier. Oh, that's way better than I thought. I thought it was like per month. Maybe it was when I joined. I think I joined pretty early on. So, okay, this free to one should be encrypted, which was in site packages. Okay, yeah. So this one's like 70 megs. So it should do for most of the files. All right. So then now we need. So our original Python 3 is dead, right? Yeah. So let's go into Windows, and then this Python should be okay, hopefully. Yeah. And then one thing I didn't do is put like any logging. So let's modify that. Here, I'm going to put this in the Windows directory, even though it wasn't letting me unzip it before because of stupid UAC stuff. Okay, recover stream. So this is just the code that I was writing in VS Code on my host. And then, okay, so maybe we'll do like this in batches to make sure all my code works. So we can do print found pt files, and then let's try this, and then pt files. Okay, that looks good. And then basically it's going to look for, oh wait, let's matched file, matched, yeah, plaintext file, matched encrypted file. Okay, so let's try that. This might take a little bit because it's going to need to enumerate the entire directory tree from // I guess we can speed it up by just giving the Frida directory here. But did it find it already? Yeah, okay. So found that. Oh, except the encrypted file path was not including the, see, I already found a bug, which is why we test. Enum pt files, enc file. That code looks fine. Why is it not including the encrypted extension. File, PT files, enc file. Weird. Like that looks all fine to me. So maybe I won't do in. No, I have to do in. That's funny though. Here I have the full path here. Might as well just use it. Oh, it's finding the recovery script one. That makes sense. How can I prevent this? How can I prevent this? I can just make sure the paths aren't matching. So, and pt file path is not equal to file os.join os.path.join root file. Okay, let's try that. Does that make sense? It was finding the non-decrypted file in the crap. It keeps finding that. Okay, so it's matching these source files. Okay, so I need to make this match better. So let's do. So the problem is these plaintext file names need to be more unique. So yeah, so I can use the file size, but it'll be the file size minus 512, which is the encrypted footer containing the encrypted key that was used to encrypt the files. So it'll be pt file size minus, no, it'll be is equal to, that's fine, is equal to file, what was the other one? os.size or something? os.path.getSize. And then this will be the pt file. Like I don't have to be doing this, but it's just making it more robust. So, and then get size of this. Okay. Minus 512. It's getting pretty complicated. Okay, let's try that. Unsupported operand types. Where's the string in here? Is this get size a it's definitely not a string. I forgot a brace, that's why. The largest plaintext file. Okay, cool, that worked. Now, let's recover the keystream. That should just work. Why is this taking so long? Because the recover keystream is only doing the XOR. Maybe we'll put in more logging as we wait. Searching for files with extension. And then we'll do that. All right, let's run this again. We're on the home stretch here, folks. Hopefully. Maybe we can look over our logic here while that runs. Maybe I can use their XOR implementation if it's faster. I don't see why this is so slow, because I'm enumerating each byte and then converting into a byte. I think I just need to be patient. Or do this with a smaller file. Decrypting file. We'll do, okay. I still don't understand why this is so slow. All right, let's just run it with the whole thing. Actually, to make this faster, what's the smallest one of these? Net standard. Oh, it's in program files, crap. Okay, you know what, that's okay. And then let's try this. Basically, I'm just gonna do a smaller plaintext file. It should still find it. Hopefully this XOR is shorter. Let me fix the other XOR as well, since that's obviously very slow as well. So we want result being, and then we'll convert this to bytes like the other one. Let's hope it works. I just want to see it rip once it finds, or once it gets the key stream. I guess it'll probably be decently slow. Hi, is possible to dev mobile app using Visual Studio and C++? I don't know. I don't do any mobile app development, to be honest, but I think there is some stuff in Visual Studio. What is your project, a game? No, I'm decrypting files that were encrypted by ransomware. Kind of niche. Okay, let's see if we can spot anything else before this finishes. Keystream, recovered file data. XR with Keystream. Yeah, looks fine. After decryption, output is game or app. There's no games or apps. This is basically like how you can recover files from a system infected with this ransomware, essentially. But game development is cool though, but I've never done any of it. Okay, let's see if then you make an app for recovering deleted data. Yeah, essentially. Yeah. All right, let's see if this actually works. Okay, so the decryptor's working now. Yeah, it's working. Instead of doing the .rec, we can just get rid of this now because we've confirmed it's working. Please explain how delete PNG files recovered successfully. What is steps? How it deleted PNG files. Oh, so it's not. So I figured out how to break the encryption that the ransomware was using. So we're actually attacking the encryption rather than trying to recover the deleted files. This is a way better than like trying to recover a file using like forensics, for example. Okay, so let's actually recover. I think that's how I get the file name. Do you know anything about cybersecurity or ethical hacking? I'm looking for a career change. Yeah, I've been in security for like 10 years. So happy to answer any questions you have. Hoshiar21, is it better to use Linux ecosystem or stay in the Windows for these developments? So I was using my host operating system, which is OS X, for the development. But now that I'm like just editing and testing this on a Windows system, which is like where the ransomware was running, then I'm just using Windows for this right now. But yeah, usually I develop on OS X. Okay, so the original file name, I think that should work. So that's reversing them. Yeah, okay, so that's correct what I did. And then we'll do, so I'm just gonna get this running and then I'll see what you guys said. Where should I start without paying thousands on school? I still need to work and feed my family. Do you have any ideas of like what kind of cybersecurity stuff you want to do? If you're not quite sure yet, do you have any experience with like IT or programming or anything like that, spookiest? The decryptor's working now. And I'm just going to start from a fresh place. Does anyone do Flare on CTF? Some of the people are doing it in our Discord. Your FOM. Here, let me put a link to the Discord if y'all are interested in joining. But yeah, we hang out there and talk about reverse engineering and malware analysis and stuff. Okay, so let's check out like these encoding files. So like ASCII.py. So these are a little bit bigger, it looks like, than our Keystream. But maybe let's see how many megs this is. So it's definitely working. How big is this file? ASCII.py, 1800. And then the recovery code needs some tweaking because I think this is the end of this Python file. Yeah, I need caffeine has gone. I need more caffeine rather. Thanks for the follow. It's going well. We're see ya, Hoshiar. Thanks for hanging out. Yeah, it's going well. We're almost done the script that we're using to decrypt files that were encrypted using ransomware. So we analyzed a cryptography flaw in this ransomware, and then now we're exploiting that flaw to decrypt files. Yeah, it's pretty fun. Okay, so recover Keystream first. Yeah, okay, that's right. No, I got it off Malware Bazaar. I can say the link. But yeah, it's kind of similar to VX Underground. Reversing large samples looks painful to me because at least looking at Geezer's decompiler stuff looks like hieroglyphics. Yeah. If you want to, here, I'll just throw this in chat because I haven't done that yet, but we do like malware analysis training stuff. So if you're interested, we teach you how to handle those big samples. I think that's just the appended encrypted original key. So what we need to do is only write the number of bytes up to so XOR with Keystream. Okay, I know what the problem is. Okay, I think that should be the bug that was causing that. Almost done, pretty much done. Just kind of adding the final little things here, and then I'm gonna restore snapshot. We're gonna re-encrypt this and then confirm that everything's working. How y'all doing? How long have you been working on this sample for? I think last weekend I did 3 hours and a bit, and then today it's been like 3.5 hours. So not very long, but it was a pretty easy sample. So not a huge sample. I'll show you. So I use Binary Ninja, not Ghidra. Hold on, I'm just gonna make sure this is working, and I'll show you Binary Ninja. So like, yeah, Binary Ninja is paid, but it's really good. So that's why I pay for it. Okay, let's see if this is clean now. Yeah, okay. So that was just the decrypted key. Okay, so let's restore our snapshot. We're gonna re-encrypt the system, then we're gonna decrypt the whole system to the best of our ability with the size of that key stream, and then we'll call it a day, I think. The training is professional, and then my day job, I also do this. Reverse engineering malware. Yeah, they have a student discount. It's like $74, I think. We also do, well, that snapshot's being taken. So this is like the course we do, and you get a Binary Ninja license with the course. Not trying to be too pitchy, but yeah, $74 is like super good for what you get. Oh yeah, let me show you the sample, sorry. So yeah, this guy had like, how many functions? I can do it in the Python console here. BV functions list. So like 800 functions, which I guess is bigger than I thought, but like the main code is only like, I don't know, 20 or so functions that we looked at last stream. And this has like a decompiler very similar to Ghidra. So we looked at all this code. Wait, I'll send you so if you're interested, we have a YouTube channel that the stream from last week is on. So you can see me like reversing this whole ransomware sample. It's this stream here, if you're curious. And then this week I'm just, I'm broke right now, but I will definitely check out the YouTube video. Yeah, no worries, man. That's all good. That's why we put out the free content too, because we know everybody can't afford training. So, okay, that snapshot's taken. So we'll do a pre-decrypt test, and then we need to copy our script here. Do you stream often or just whenever you feel like it? I've been streaming, like I try and stream like every couple of weeks. But recently, this summer, I was really busy, so I didn't get to stream as much as I wanted to. But this is like, I streamed last weekend, and then I'm streaming now. So, that's like the most frequent I've done, basically, is once a week. Let's see. But yeah, always happy to answer any questions you might have if you're doing malware analysis. Okay, let's copy this over to our protected directory. And then I still need to edit this. We still need to encrypt this system, run past all exceptions. All right. We'll try and catch other streams. Interesting to watch. Cool. Yeah, that sounds good. And then I record all of them too. So all of them go up on that YouTube channel I just sent. So this is being recorded right now. And then usually I edit it down substantially with all the pauses and stuff. And then so it gets quite a bit shorter. This should be done pretty soon. Let's run our script. Oh yeah, it's gonna restart. So annoying. What got you into malware analysis specifically? So I went to school for information technology. And then once I finished that, I was doing some like quality assurance. I was always interested in security. And then I ended up working for a startup that was doing like kind of like an early endpoint detection and response, and basically like an antivirus product. And I was doing quality assurance for them. And then just because I was working with malware all the time, I ended up doing malware analysis on my own. And then eventually I moved into a research position, and then started doing malware analysis there full time. So, okay, let's go to Python, and then recover stream, PT files, C. Yeah. Before that, I did some like web application penetration testing and some other stuff that was similar to security, or within the security field. But I like malware analysis more because there's kind of always a goal that you're working toward, and it's kind of always fulfilling because once you figure out what some malware is doing, you can always, or there's always more you can analyze. Whereas like some web apps are like get more and more secure to the point of not being able to find stuff. What was the issue here? Memory error. Crap. Why does Python suck? Let me fix that again. Okay, let's try that again. Do you use INetSim or something else? Yeah, I use INetSim and FakeNetNG as well. Users. Or wait, Windows. Recover stream. Python. So we have our PT files, and then // Is there a major difference? I kind of like FakeNetNG because it's written in Python, whereas INetSim is written in Perl, and then INetSim doesn't support like the most recent SSL suites. So if your malware is using like HTTPS, for example, then sometimes it doesn't always work, but it works with FakeNet usually. It's because it's old and it's Perl. So I'm sure somebody could update the Perl, but I don't know any Perl, unfortunately. I use the Frida file as well in this case, just because it is bigger, so it will be a larger keystream, and then we will be able to recover more files. Like other things that I can put in place are like checks to make sure that the file being recovered is not larger than the keystream and stuff like that. But for all intents and purposes, I think our 4 gigs of memory is being used. Man, Python, crazy. That's probably why it's so slow, because it's probably swapping. Like how much memory is it using? 3,000 megs. Yeah. This is kind of weird because I'm using, these are just like Frida files on disk that were encrypted by the ransomware, so I'm not actually using Frida. But they came with, so I'm using Flare VM. So this Mandiant thing. And it ships with Flare. Oh, cool. Yeah, you're aware. I have one VM. Nice. Okay, hopefully this works. So one test that I'm gonna do is see if my original Python will work. Because in theory, if this can decrypt all the Python files, then my original Python install should work. But yeah, so our decryptor's working. We'll do a few tests after this, but not bad. Like 3 hours and 45 minutes to go from, I got the decryptor working, so it's just running now. But yeah, 3 hours and 45 minutes from kind of analyzing the crypto flaw to writing a full decryptor. Yeah, it wasn't really speed run. Like all in, this was like 7 hours of work as like me articulating it on stream. So I guess it would be quite a bit faster me doing it on my own. But all right, why don't we look at some of these files, because this is taking a while. So like this GeoIP flow thing. So like this is a pretty big Python file, and it's fully recovered. This rdump file, again, fully recovered, and then no crap at the end. So I think everything's working. these large file decryptions are going to take a while because like it's basically going to be the Keystream recovery time plus that. So I don't know if I'll be able to test the Python stuff. We'll see how long this takes. But yeah, we can look at what else was decrypted here. It's basically just been all the Python stuff. PYD, LZMA, this license file. So the bug in the malware algorithm was the key reusage. How does the malware generate the key in the first place? Was there no way to attack that, or was it's just faster? So yeah, we can look at that. So this is the MWGen key function, and it uses crypt acquire context and then cryptgen random, and this cryptgen random function is a Microsoft Windows API, and it's cryptographically secure. So and then it's generating 120 like 16 byte key, and that key space is like really big. So it's like pretty secure. But the key like the known plaintext attack basically let us crack it. So there's so many Python libraries. But yeah, while it's running, I'll just throw our Discord in the chat again if anybody wants to join. So you had the secret key for the encryption algo. No, it's like recovering the... Here, let's see if I can pull up those slides again. So this is how the stream cipher works. And basically there's a key generator, the plaintext file. It encrypts it using XOR after the key stream is generated, which is this, and it produces the encrypted file. But if we have the plaintext ciphertext, if we have the plaintext and ciphertext, we can recover this key stream part, which is basically the last thing we need, or which is basically the last thing that's XOR'd with the file to encrypt it. So basically we're recovering like a later stage in the encryption algorithm. We're not recovering the original key. So yeah, hopefully that makes sense. Yeah, it's just going to take forever to recover all these. Yeah, it's fire. Straight fire. But yeah, feel free to hop on the Discord if anybody wants to hang out. If you want to learn how to use Binary Ninja, but we have a whole course on it now. We also have a course on IDA. And then it's not just malware analysis on those things. It's on learning x86 assembly, doing full static and dynamic analysis of both native Windows binaries and .NET assemblies, doing network analysis, so like analyzing network protocols that we were just talking about earlier, obfuscation, so analyzing more encryption algorithms than the one we looked at today, which was Salsa 20, unpacking and process injection, and then doing comparative analysis, so comparing different malware files against each other that are part of the same malware family or similar, and then writing YAR rules and stuff like that. So yeah, I just wanted to mention that. This whole decryption is going to take a while because it's just still decrypting the Python stuff. So I'll probably just call it. But thanks all for joining and hanging out. This was really fun. And I'll put all this code up on GitHub, and I'll tweet about it and put it in the Discord channel and stuff. So if y'all want to check out the code. And then again, this Binary Ninja database is available to our premium students. And yeah, hopefully we can do more ransomware decryption stuff in the future. Maybe we can do some core stuff on it at some point, but it's always a fun time. So thank you all so much, and I'll talk to you later.